Something wrong with my settings. I just have to make an adjustment here. Screen layout. Tile. I don't know why that is. Okay. All right. So let's start off with homework. So Mayan, you have 3.1, 25, and 26. So let me present that. All right. 3.1, 25. All right. Okay, so here in 25, they gave you this function. They want you to find the critical numbers. So what did you do for this?
So first, well, what they gave you was 2x to the third minus 3x squared minus 36x. So first I took the derivative of that whole thing, which got me 6x squared minus 6x minus 36.
Right.
And then I set it to 0 because that's how we'll find what the suspects are for the maximum and the minimum.
Right.
So I factored, and then I got x equals 3 and x equals -2.
Perfect. Yeah. Okay. So these are what they call, the book calls the critical numbers. We used to call them the critical points. And these guys are going to be suspects for where you might find a max or min. Okay. You actually did more work than they asked for here, right?
Yeah, I only realized afterwards.
Yeah.
Do you want me to continue explaining, or?
Well, no? Okay. Yeah, you plug these points into the original function, right? To see what the y value was at these 2 points. And so that pretty much tells you that, let's see now, when you plugged in 3, you got that the y value is minus 81. And when you plugged in minus 2, the y value is 44. So, probably 3 is the minimum, 44 is the maximum. Okay. That's pretty much, oh, I'm sorry. You did more. I forgot. Yes, you did a lot more, actually. You actually wanted to see specifically were these mins or max. So what did you do here? You have these 2 critical numbers, critical points, and you wanted to get an idea which was the min and which was the max. So actually, what did you do here?
So what you want to do is try and create the picture for yourself about what it's going to look like, because then you can visualize it. So similar to what we did in class, you take numbers that are below your critical numbers and above your critical numbers. And then also you can take one in the middle just to get a better visualization.
Right.
And then after you the third and fourth columns, I guess you could call them, that's after you plug the numbers in. So after I took the numbers, I plugged them in, and then you can get a picture. So you can see from that little picture down on the right, where the maximum and minimum is going to be. You see -2, it's going in the positive direction. So that's going to be the maximum. And then for 3, it's going in the negative direction. So it'll be the minimum.
Right. So what you did was you basically, that the critical points here are 3 and -2. So you picked a convenient point on either side of -2, like 0 and -4. You could have picked -1 and -3, whatever. And you find out what the derivative is on. Is that how you did it? Yeah, you saw what the derivative was at those points, correct? And we have a positive derivative, the graph is going up. We have a negative derivative, it's going down. So you see for this critical point number at -2, the graph must be going up to the left of it and down to the right of it, which means that at -2, you're at the top here of the mountain, so to speak. So that's going to correspond to a maximum. And then over here for the critical point 3, you saw that the derivative to the left of it was negative, but the derivative to the right of it was positive. So the curve is coming down, going through x equal -3, and then coming up. So that tells you that this point, x equal 3, the y value is sitting at the bottom of like a little valley or something. So that's going to be a minimum. Okay, so yeah, this is one way we can do it. This is even much more work than it was required here, but it's certainly it's good, and it's very nice work actually. And we're going to learn maybe today, if not next time, an easier or better way to actually get sort out whether your critical point is a max or a min. Okay, but this is very, very nice. More work than they asked for, very commendable, very nicely done. Okay, so any questions? The only other comment I'll make is, these are the critical numbers or critical points. Remember, there's one other way you can get a critical point or critical number, and that's where the derivative does not exist. So in this course, we're not really going to see that much, but in this particular problem, the function is a polynomial. Polynomials are always differentiable, meaning they always have derivatives at every point, so we don't even have to worry about that. Okay? So that would take care of that. All righty. Any questions on this? Very, very nicely done. Okay, and you also did number 26, the one after it.
Yeah.
Okay. All right. This time I am prepared. I got them set up correctly. Okay. All right, so here they give you this function, 2x cubed plus x squared plus 2x. Same story, find the critical points. So you went ahead and took the derivative. The one thing I would say is whenever you're writing equations, it's best to try to full equation so everyone knows exactly what they're looking at. So I would have written f prime x equals over here where my arrow is. Okay, that way people know exactly what you're looking at. Okay, so you took the derivative and you set equal to 0. And then what happened?
Yeah. So then I tried to factor it like I did the other one, but I got stuck.
Yeah.
Because it's not factorable. So I used the quadratic equation instead.
Very good. Yeah, everyone's got to know the Okay, yeah, everyone's got to know the quadratic equation. Negative b plus minus the square root of b squared minus 4ac over 2a. Remember, the 2a is the entire, goes underneath everything. This fraction line goes through everything, right? So you plugged it in, and you ended up with x would have to equal this thing. Remember, this means we'd give you two different roots, -1 plus the square root, -1 minus the square root. But what's the problem with this thing here?
So the problem is that the inside of a radical can't be negative. So, right. There's no critical numbers because you can't do anything with that.
Right. Okay. Yeah. This is excellent. Let me say a couple of words about this here. Okay. So this particular function has no critical points. Now, and again, this is a polynomial, so there's always a derivative, so you don't have to worry about that. So this is simply a function that is not going to have any critical points. All right. Let me just make a quick comment here. First of all, I'm going to just put my screen on. If you look at a graph of the derivative function, okay, which let me just bring that up, which I already actually did here, but let me just switch this off. Okay, let me get rid of this. Let me stop presenting. All right. And let me actually turn on the camera here. Boy, this is such a pain. Oops, not there. The settings for so you can look at this. All right. Okay, so I actually already put this thing into the calculator. This is the graph of the derivative function, okay? And if you look at the graph here, you see that the derivative function has no roots. It doesn't go down to the x-axis, okay? So this is consistent with what you found when you put in the quadratic equation. You couldn't come up with any real roots, okay? So there are no critical points. Again, this thing you're looking at is the graph of the derivative, okay? 6x squared plus 2x plus 2, that function, not the original function, okay? If we look at the original function, let's just graph the original function. So again, you go to press y equals, that lets you input the function. The original function here was 2x cubed, so it's 2 times x cubed, okay? I'm sorry, whereas 2x cubed plus x squared plus x squared plus 2x. I gotta start, I'm sorry. Okay, 2x cubed. By the way, when you just multiplying x by a number on the calculator, you don't have to put in times, just 2 and x. It'll understand that. 2x squared plus x squared plus x squared plus 2x. Okay, so this was the original function, 2x cubed plus x squared plus 2x. Let's see what the original function looks like. Okay, so this is what the original function looks like. It's kind of similar to y equal x cubed. It is a cubic polynomial. And when you look at this, you realize this makes sense because it is not going to have a max or a min. The function is coming up from minus infinity and just going all the way up to plus infinity. Okay, there's no place where where you're going to have a max or a min for this function. Okay, so graphing this out is often a good way to confirm your algebraic work and make sure you're on the right track here. All right. Okay. All right. Let me just say one other word about this. When you do the quadratic equation here, you come up with the discriminant b squared minus 4ac is negative, which would give you the square root of a negative number. And therefore, we're saying there's not going to be any roots. But let me just qualify that a little bit because it's an important piece of mathematics everyone should know. What it's really just telling us is there are no real number roots. However, there are imaginary roots, okay? Which in fact are given by exactly that, square root of minus 11. Now, you don't have to worry about imaginary numbers. If you've seen them, that's nice. If you haven't, okay, they're not that imaginary. But I'm just going to point out there is a very famous theorem called the fundamental theorem of algebra, which everyone should have heard of or should hear of at some point if you're taking this level of math. The fundamental theorem of algebra says that every polynomial has a root. In fact, every polynomial of degree n, the degree is the highest power term in the polynomial. Every polynomial of degree n will have n roots. Okay, so every polynomial that goes up to x squared actually does have 2 roots. Okay, the only problem is they may not be real numbers, but they have roots. And this is called the fundamental theorem of algebra. And we're just seeing that it has no real numbered roots. It does have 2 imaginary roots, okay? Every polynomial is going to have roots, but it's just not, they may not be the real number, a real number. Okay, so that's called the fundamental theorem of algebra. It's something worth hearing if you're going to continue in math. The fact that it's called fundamental tells you that it's important. Okay, that's where it gets the name from. Okay, all right, very nice work. Thank you. Okay. I just want to look at something here. No, not this. Ah, okay. All right. Okay, doke. The other homework problem person is not here. Okay, so right, that's it for the homework for today so far. All right. Any questions? No? Okay. All right. In that case, I want to move onward, and let me just put away my homework sheet here and get out my notes. Sorry. Okay. All right. So we're now in chapter 3. We did an example, a Maximin example the other day. Not the easiest problem, not the most elegant. Okay. What we're going to be doing now is next section here is we're going to introduce some of the most famous theorems in all of math, and they're extremely important theorems. The title of the section, I believe, is called the mean value theorem. That's one of the most important theorems in all of mathematics, one of the most important theorems in all of calculus. So we will spend some time on it, okay? And what comes out of that, the consequences of this theorem are significant. There are a lot of important facts that come out of it. So here's how we're going to start this off. We're first going to prove a theorem that's easier than the actual mean value theorem, which is the ultimate objective. And this is the way we often do math. We actually try to prove something much simpler first, and then see if we can use it to prove something even more complicated. So this is going to be a theorem known as Rolle's theorem, R-O-L-L-E-S. I've heard it pronounced in all different ways. Raleigh's, I don't know, Rolle's. Usually Rolle's is the pronunciation. So Rolle's theorem deals with the following situation. Suppose we have a function that's continuous on some closed interval from, say, x goes from a to b. The function is continuous on that closed interval, and the function is differentiable on the open interval. It's differentiable on the open interval. Now, there's a slight difference between these two things here. The difference, we're looking at the same interval, but what we're saying is we don't care if the function has a derivative at the actual endpoints, x equal a and b. We need it to be continuous at a and b, but we don't care if it has a derivative at a and b. Between a and b, though, it has to have a derivative everywhere. Okay? All right? A very important question should come up in a minute, or I'll bring it up right now. Why do we have to be so picky here and make this distinction? Because after all, if we just said that we're going to require our function to be differentiable on the closed interval, in other words, differentiable including at a and b and everything between, then we know it's going to be continuous. Then we know it's going to be continuous. So why do we have to make this distinction? Or why do we want to make this distinction? And there's a very specific reason, which I'm going to show you an example once we do the theorem. By the way, the first time I ever taught this course, many, many, many years ago, a student asked this question when I was presenting it. It just so happens I was also being observed that day by the chairman of the department since I was a new teacher. And I had the answer for this question very quickly, which impressed the chairman. No, that was good. Okay, but this is an excellent question that student asked, and I'm going to ask it also, and we'll discuss it when we go through the theorem. if I just say, make life easier and say, just make it so that I want a function that's differentiable on the entire closed interval, I no longer have to worry about saying continuous, because anything that's differentiable is automatically continuous. Why am I making this extra effort to split the two conditions and saying we're willing to forego it having a derivative at the end point? And there's going to be a reason. The main reason being is that there will be functions that satisfy this theorem, but they don't have derivatives at the endpoints, but the conclusions of the theorem still work. So we want to be as inclusive as we can. When we prove theorems in math, we always want to put the least conditions needed on the situation, because the least conditions you have, the more functions you can include in the result. It's a more powerful theorem. It's a more general result. And I'll show you a specific example when we go through the theorem. The theorem itself is pretty simple. Remind me if I don't get to it, please, someone to show you this quick example. All right, so we're setting up the scenario. We have this function y equal f of x. It's continuous on some closed interval AB. It's differentiable on the open interval AB, meaning we don't care if there is a derivative at the endpoint, okay? But everywhere in between there has to be. And the next condition we're saying is that it has the property that f of a is equal to f of b. What that says is that the y value at the beginning of the interval is the same as the y value at the end of the interval. That's what that's saying. And then we're going to have a conclusion here, okay? The conclusion is going to be there must be some point C, right? This symbol means implies. There exists a point x equals C that's in the interval AB, the open interval, where such that the derivative at C is 0. So let me give you a minute to write this down and now explain what that means in words, okay? Because that sounds a little bit vague when you first hear it, okay? What this is saying is that if I have this situation, these conditions, it's continuous on the closed interval, differentiable on the open interval, and the y value at the beginning of the interval and at the end of the interval are equal, then somewhere between A and B, the derivative has to be 0. There must be some place, we're calling it at the point x equals C, where that derivative must be 0. And if we look at the picture here, it becomes blatantly obvious why that's going to be true. So let me draw out the situation here. We have a point here A, we have a point here B, and here's f of A and f of B, and we're saying the y value is the same. These are on the same horizontal line, right? The coordinates at this endpoint are B comma f of B. The coordinates at the beginning are A comma f of A at that point. So the function starts here and it ends up at the same y value. So let's just consider, how could the function run from one end to the other? Well, one possibility is that the function first starts to go upward like that. But in order to end up at the same y value, it's going to have to come back down. And where it comes back down, it has a turning point. Okay. And since the function is continuous and differentiable, we know that turning point cannot be a cusp or a right angle or anything screwy like that. It's got to be a nice smooth turning point. So right here at this turning point, the tangent line is horizontal. And that means that for this x value at this point, the derivative is going to be 0. So this is just a picture proof. It should be clear that if you start and end at the same y value and your function goes up first, it's got to come down. Where it comes down has a turning point. At that turning point, derivative is going to be 0. Okay? That's the point C. How else can this function run from A to B? Well, instead of going up, it could go down. But if it starts off by going downward, it's going to have to turn around in order to come back up and end at the same y value. So there's going to have to be a turning point again. And where you have that turning point, the derivative is going to be 0. All right? So again, if you travel from point A to B by first going up and coming down, or first by going down and coming up, either way, this function must have some point, some place where the derivative is 0. There's only one other last possibility of how the function can run from A to B, and that is if it's a straight line, like if it's y equals 5. Obviously, though, if it runs from A to B as a straight line, then it certainly has points in between where the derivative is 0, because the derivative of a straight line is 0. Yes, someone's pointing out that what goes up has to come down. Yes, okay. Or what goes down has to come up also. Okay, so there's no other way clearly that this function can run from A to B and start and end at the same y value unless it has a turning point or if it's a flat line. And in all three cases, we see that, yes, the derivative must be 0 somewhere in this interval. And this is what Raoult's theorem says, okay? All right, you may not think this is too dramatic or interesting. What's the big deal? This is gonna be a big deal. Let me even show you a little picture I usually use when I present this in class, okay? So we're gonna see this, you're gonna see this picture again, because this is not the main purpose of it. But this is the scenario I drew. This is x equal A, x equal B. The y value at A and B are the same. That's why they're on, I drew that line across. And this is the situation where first the function goes up as its turning point and comes back down. And at this point where it turns, that's the point we're going to call C. The derivative there is 0. Okay? All right. Now, this theorem, though, is not the biggest thing, but it already lets us do something rather interesting, which may not make some of you too happy because it goes back to a kind of problem we've done. Let me also just point out before I do this example, you must memorize these conditions because the main thing we're headed to is called the mean value theorem, has the same first two conditions. Continuous on the closed, differentiable on the open. That should be something that you memorize so well that if someone shook you awake at 3 in the morning and said, quick, state Raoult's theorem, you should be able to say immediately, continuous on the closed interval, differentiable on the open interval. You're going to just be repeating that over and over and over. Okay? Yes. That's the laughs. All right. So let's do an example. This is an example in the book, example 2. And this is actually a pretty hard example if you've never seen it like this. It's going to combine a bunch of stuff we know, but it is a standard problem in this course. So here's a function, and the function they give us is x cubed plus x minus 1. All right. Normally, I try not to just do the examples in the book, but this one's worthwhile. And it's one of those examples that if you just try to read it yourself, you may end up saying, huh, how did that happen? It's not an easy problem, but it's a very educational, important problem. It is the kind of problem that often would show up on an exam. Okay, all right. And here it is. Show that this function has exactly one real root. show there is exactly one root. Real root, again, meaning a real number. As I said before, the fundamental theorem of algebra tells us this function actually has three roots. There's only going to be one real root. The other two will be imaginary numbers for the roots, but we don't care about that. Again, remember what we mean by a root. A root is a value of x that when I plug it in, I get y equals 0. That's a root. It's also sometimes called the zero of a function. All right, so this problem is asking for a lot. It's asking us to show not just that there is a root, that you already know. You had that kind of problem on the exam. But it's now asking you to show it has exactly one root. Okay? So, in order to show that there is exactly one root, we first have to show that it has one root at all. We have to show that it is not a kind of function where there are no roots, or no real roots. So our first job is basically to redo the same thing we did with the intermediate value theorem here. We have to show you that there is a root. In order to show there's only one, I first have to show you that there is at least one. So that's a job for the intermediate value theorem. What's particularly difficult about this problem is they're not telling you a hint by giving you the interval. You got to decide, you got to be able to show me that there's an x value and another x value where the thing changes sign. And then we can use the intermediate value theorem. Okay. So there's some guesswork and luck in these kind of problems. So let's look at f of 0 and x is 0. So if I plug in x equals 0 to this function, I get y is minus 1. And suppose I plug in x equal 1. Well, that's going to give me 1 plus 1 minus 1. That gives me 1. So I've already found that there is one interval at least where the function goes from negative to positive, namely the interval 0, 1. Now, notice that we didn't give you this interval. You had to figure it out by guesswork and luck. And that's really what it often boils down to. Usually what you do is you pick some easy numbers and plug them in, and hopefully you'll find that at one number it's positive and the other is negative. In this particular case, if you just stare at this function, and you're talking about easy numbers, 0 is always an easy number. If you plug in x equals 0, you see it's going to be minus 1. And then you see that this is x minus 1 here. So if I plug in x equal 1, those two will cancel, and I'll get plus 1. In any event, it takes some guesswork. It really does. Sometimes you may need a calculator, graph on a calculator to see where might there be an interval where the function changes from plus to minus or minus to plus. One of the things that, again, that makes this problem hard is they don't give you the interval. You have to go searching for it and hope that you come up with an interval pretty quickly. Okay. Now, we now have a function. We're trying to show it has at least one real root. Well, we have an interval where it goes from minus to plus. And we're going to use the intermediate value theorem to come to that conclusion, but we have to state, again, that it meets the conditions of the intermediate value theorem. And the intermediate value theorem here just says it's got to be continuous on the interval 0, 1. Well, it's a polynomial. Polynomials are always continuous everywhere. Okay, so we're in business. We have a function that's always continuous. In particular, it's continuous on the interval 0, 1. We know the function changes sign from minus to plus. So now we conclude by the intermediate value theorem that there is a root. There exists a root in this interval. By the way, this is the symbol for exists that you see in all math books. This kind of backwards capital E. That's a symbol that we use to write exists. I'll start writing it because it's too much to write out a word with 6 letters. I'll just write the 1 letter. Notice, by the way, you had to point out that it is continuous, and that lets us use the intermediate value theorem. That's required. Okay, so I've already shown you now that this function has 1 root, at least. But the problem is not satisfied that. The problem is asking us to show there's only 1 root, exactly 1 root. And that's a challenge to answer that question. And there's some good mathematics involved in here. And what you're going to see is a very standard mathematical proof to show that there is only one of something that you're dealing with. And the way we deal with this problem in general, when we need to show, okay, I know there's 1, let me show that there's not more than 1, is to do what's called proof by contradiction. A proof by contradiction means we're going to assume the opposite. We're going to say, okay, let's pretend there are 2 roots and follow that to its logical conclusion and see what happens. So, and I'm going to leave the sentence hanging at that. So what we're going to do now is to show that there's only 1 root, to show exactly 1. We're going to assume there are 2 roots. Assume there exist 2 roots. We'll call them at x equal a and x equal b. This is not the same. We're not using a and b otherwise. Now, by definition, if x equal a is a root, that means that f of a is 0. If x equal b is a root, it means that f of b equals 0. And we're assuming this function has 2 roots now. Okay? Now, this is interesting because that means that I now have a point A and a point B where f of A equals f of B. Okay? And we're dealing with a polynomial, and a polynomial is always continuous and always differentiable. So if I just look at the interval a to b, I have a function where the y value at the start and the end is the same. F of a equals f of b. The function's continuous differentiable on the entire interval. That means Raoult's theorem can apply. That means we have the condition for Raoult's. So just look back to what we wrote before. That's the condition for Raoult's. It's continuous on the interval AB, it's differentiable in the open interval AB, and we have f of A is equal to f of B. Well, that's exactly what you need to use Raoult's theorem. So by Raoult's theorem, it says there must be a point C. There has to be a point x equals C in the interval AB where the derivative at that point C is 0. That's what Raoult's theorem says. There has to be some place where the derivative between A and B is 0. Well, let's look at the derivative of this function, but the derivative of this function is 3x squared plus 1. And we're saying that somewhere this derivative has got to be 0 by Raoult's theorem. Well, if I say set this equal to 0, I now see I'm looking at a major problem. Does anyone see what the major problem is here? What's my problem right now? Well,
It's higher than
yeah, yeah, there is no solution. There's no real number solution here. The reason is that x squared is always greater than or equal to 0, plus 1 means it must be greater than 0. This will never give you a solution. I mean, if you subtract 1 from both sides, you get 3x squared is minus 1, x squared is minus 1/3. That has no solution. But the problem is Ralph's theorem says it's got to have a solution. It's got to have a place where the derivative is 0. But I'm showing you such a thing cannot happen. What I'm showing you is that if we go back and assume that there are two roots at A and B, one at A and one at B, and we follow the logic to its conclusion, we come up with a contradictory answer. On one hand, Ralph's theorem says the derivative has got to be 0 somewhere between A and B. But when I actually look at the derivative, I see that can't happen. Okay? This derivative can't be 0. Well, that's a contradiction. Ralph's theorem says the derivative's got to be 0 somewhere. The derivative itself says, heck with you, I'm never 0. That's a contradiction. And it means that something's wrong. What's wrong? Well, what's wrong, if all the other work is correct, which it is, what's wrong must be your original assumption when you said, let's assume there are two roots. That's what's wrong. Everything else, the work is correct from here on in, but it's giving us a complete contradiction. It means that whatever you assumed at the beginning has to be wrong. We assumed there were two roots. It can't be. Because we know Ralph's theorem is true, and we know it's also true that this derivative, 3x squared plus 1, can't be 0. So the problem is back at the original assumption. We assume there are two roots. This is telling us by this contradiction that there cannot be two roots. There can't be two roots. And this we call a proof by contradiction. And this is a very standard way of proving things. Proof by contradiction. And a proof by contradiction is just what you saw. You assume the opposite of what you really want to show. And then you show that that assumption leads to something impossible, which means your assumption's wrong. So we've actually now solved the problem. We showed that there is one root with the intermediate value theorem, and now I've just shown you there cannot possibly be more than one root. And that's exactly what the problem asked us to show. Show there is exactly one root. We've done that. Okay. If you've never seen this kind of proof before, it's going to take a little bit of thinking and mulling it over at home and studying this a little bit more. But this is such a standard proof. It is used all over the place endlessly to prove that there's only one of something. Proof by contradiction. And also to prove other things, by the way, to prove things that are just not true. If you continue in math, you will see this done over and over and over and over and over and over, just endlessly. And it's something you need to know. Yeah, sure, Mayan, what's the question?
So after you wrote to show after you wrote like the proof by contradiction, we're going to assume the opposite, that there are two roots. How did you then get the f of a equals 0, f of b equals 0, like that thing?
Okay. We know, I'm going to try to ultimately show there can't be two roots. The way I do that is I'm going to assume there are two roots. and show that that causes trouble. Okay, that much you got, right?
Yeah.
Okay, we're going to call the two roots x equal a and x equal b. The point A and the point B, those are the two roots, right?
Yeah.
That I'm pretending exist. But by the definition of root, if a is a root, f of a is 0.
Mm-hmm.
A root means I plug in that value for x and y is equal 0.
Mm-hmm.
And if b is a root, f of b is also 0. That's what it means to be a root.
Right.
You buy that, right?
Yeah.
Well, if f of a is 0 and f of b is 0, then f of a equals f of b. They both equal 0.
Oh, I see.
Pretty slick, huh?
Yeah. Smart.
Nice little trick.
Yeah.
And the neat thing about this is that, but this is precisely what we need to bring in Raoult's theorem. We need a situation where f of a equals f of b. Okay?
Yeah. Thank you.
Okay? This is not easy. And that's what I said. I don't normally like to do the examples in the book because you should be reading them yourself and studying them. But this is not such an easy example, particularly if you've never seen this kind of stuff before. This is worth spending time on. I feel this is not an easy proof. Okay. Have many of you seen this often, or have most of you not really seen something like this? Has anyone really seen this? Or for most people, is this kind of a new thing? Why don't you say in chat? Okay, so some people have seen it in other courses, but yeah, very often this is a new thing. It takes a lot of getting used to. Okay, it's not such an easy thing. Oh, so okay, Richard. So you learned something very important and new. Okay, very good. Okay, so this is an important concept, and as I said, I'm doing the example carefully. It's in the book because I don't think reading the book gives you the full flavor. Okay, it's a slick method. Okay, all right. We're gonna move on. Means you guys got a lot of studying to do now on this. Okay, get comfortable with this, and particularly learn the theorems. Now, Raoult's theorem, though, is not the main course here. It's like the smorgasbord at the beginning, the appetizer or something. Raoult's theorem is not the real big deal. The real big deal is the theorem that we're coming to now, which is known as the mean value theorem. That's the real deal, and that's the big deal. Okay. Oh, let me just finish. See, no one reminded me. I told someone to remind me about Raoult's theorem. I said I would give you
I have a question.
What? Go ahead.
Sir, the condition for Raoult's theorem included differentiable in the open interval AB, but how did we conclude that? Because all polynomials are continuous, but we know we cannot conclude anything about their differentiability from the continuity.
No. Okay, you gave me that. All polynomials are also differentiable. It's just that conclusion doesn't come from the fact they're continuous. It comes from a separate proof. And you know what the actual proof is? That the derivative of x to the n is nx to the n minus 1, and all polynomials consists of chunks of x to the n. Okay.
Oh, I see.
Okay, I'm
Yeah.
making a very clear distinction.
Got it, sir.
All polynomials are differentiable everywhere, but you can't make that conclusion from the fact that they're continuous. It's a true conclusion, but it doesn't come from the fact they're continuous. It requires separate proof. Okay?
I understand, sir. I got confused because of the question in the exam. I remember. Got it, sir.
Okay. All right. So let me give you an example, though, of why we are careful to make this kind of a distinction. Let's look at a semicircle. Y equals square root of 1 minus x. So this is an upper semicircle of radius 1. Now, you notice that this particular thing here, it is continuous on the closed interval, minus 1, 1. This point is x is minus 1. This is point plus 1. But it's not differentiable at the end point, because at the end point here, the tangent line to the curve is vertical. This is an example of the type we've seen that's not differentiable. So it's only differentiable in the open interval. And sure enough, Raoult's theorem applies. In fact, the point where the derivative is 0 is right up here at x equals 0 at that turning point. Now, here's the thing. I said before, why don't we not worry about distinguishing between continuous and differentiable and just say Raoult's theorem, for Raoult's theorem, we're only going to need it to be differentiable on the closed interval, then we don't have to talk about it continuous. It's automatically continuous if it's differentiable. Why do we bother to make such a distinction between the two things just about when we're only splitting hairs on the endpoints? Well, you're looking at such a reason. You see, this function does satisfy Raoult's theorem. But if we insisted that it's differentiable at the endpoints, we could no longer use Raoult's theorem, even though Raoult's theorem works in this case. It means that there are many functions where Raoult's theorem would work, but we suddenly wouldn't be able to use Raoult's theorem if we made our requirements stricter, harder. So that's why we don't want to say for Raoult's, forget about breaking up continuous and differentiable. We do not want to say, just make it differentiable on the closed interval, then automatically it's also continuous on the closed interval, okay? We couldn't make life easier that way, but we're throwing away a lot of good functions where Raoult's does work. And that is why we split it up into the difference between continuous and differentiable at the endpoint, because Raoult's will work even if you do not have a derivative at the endpoint. And we don't want to make the requirements for this theorem any more difficult than they already are. I don't want to insist that there is a derivative at the endpoint, even though it would be a lot easier to memorize and think about. Okay? All right. That's a fine point. There's an excellent question that student asked me. And as I said, thank goodness it was one of my first terms teaching, and the chairman was sitting there observing me. And thank goodness I had the answer at my fingertips, even with this example. I'll never forget that day. Okay. All right. So he didn't find me. Okay. All right. Now we're going to come to the real deal here. We're going to come to what's called the mean value theorem. Okay. And the mean value theorem is going to look very similar at first to Raoult's theorem. It's always abbreviated MVT, the mean value theorem. And once again, we're going to start with some function with the exact same conditions. It's going to be continuous on a closed interval AB, and it's going to be differentiable on that open interval AB. Those are the same two things. Mean value theorem. MVT is mean value theorem. There's a reason why you're going to use the word mean also. Mean is the same as average, right? Mean value theorem. You notice we're using the exact same requirements as Raoult's, okay? But now we're not going to require f of A to equal f of B. We're going to come up with a very different conclusion here, okay? And the best way to show you what the conclusion looks like is by looking at a little picture. So let me draw in such a function. And I'm going to draw it in to look sort of like this, where this is A, and that endpoint is B. Okay. And now I'm going to connect the dots from these 2 points in a straight line. In other words, I'm making a secant line. I'm drawing in this straight line from the initial point to the end point. The function itself is the curve, but I'm drawing in a straight line. because I want to use it for something. Now, let's think about what happens if we start here and travel up the curve going to the endpoint, okay? In terms of the tangent to the curve. Let's think about this in terms of the tangent to the curve, okay? What's happening to the tangent line to the curve? Okay, so I need a smaller piece of paper than I have, really. All right, I'll just use this for a minute. So we're going to walk up this curve, and at each point, we're going to look at the tangent to the curve. So over here, the tangent to the curve would look like that. Moving a little more to the right, the tangent now looks like that. Moving more to the right, the tangent looks like that. More to the right, the tangent looks like that. Okay? More to the right, the tangent looks like that. More to the right, the tangent looks like that. Right? Everyone agrees this edge is the tangent to the curve. But we passed something very interesting. Something interesting happened as we kept watching this tangent line as we went along the curve. And the interesting thing occurred right about over here. Because if you look carefully at the tangent line to this point, right about there, you see that it seems to have a relationship to this dotted line that connects the endpoints. Namely, it's parallel to that line. Everyone agree? Everyone convinced of that? Just looking at the picture? Okay. In fact, if you think about it, this progression along the curve leading to this endpoint is always basically going to work so that at some instant, if you keep drawing in tangent line, there's going to be a tangent line that's parallel to the line connecting the two endpoints. And this is the crux. This is the statement, really, of the mean value theorem. Very loosely in words, is there has to be a point between A and B where the tangent to the curve is parallel to that secant line that joins A and B. Everyone buy that? Everyone buy the picture? Okay. Well, what do we know about parallel lines? There's something very important we know about parallel lines. I mentioned it, I think, a week or two ago, and we mention it again. What is the relationship? What's the algebraic relationship between parallel lines? Everyone should they have the same slope. Thank you. They have the same slope. Parallel lines have the same slope. Okay. So this is the point up there, x equals c, where the tangent to the curve is parallel to the line connecting the two endpoints. Okay. Well, what is the slope of this straight line? Well, it's the change in y over the change in x, isn't it? In other words, it's f of b minus f of a over b minus a. Isn't that the slope of the tangent line? Of the, not of the secant line. Right? And at the point C, what is the slope of the tangent line? Well, the slope of the tangent line is the derivative at C. Remember, everyone's got to know that's a geometric interpretation of derivative. It's the slope of the tangent at that point. So what we're saying here is these two lines are parallel. That means they have the same slope. It means that this expression f of b minus f of a over b minus a, which is the slope of the straight line, has to equal the derivative at the point C, because it's the same slope. Okay. Sounds reasonable. So here's the statement now, the mean value theorem. If we have a function that's continuous on the closed interval and differentiable on the open interval, okay? All right. Then we have the following conclusion. All right. 1 second. I'm sorry. I forgot to turn off that my phone. What? 1 second. I'm sorry about that. Okay. It's continuous on the closed interval, differentiable on the open interval. We get the following is true. So there must exist a point x equals c in the interval AB where the following algebraic statement is true. F of b minus f of a over b minus a is equal to the derivative at that point c. There must be some place between a and b where there's a point where the derivative is equal to the slope of that line. We're all in agreement with that. Yes? Okay. Now, this actually is not that strange or foreign to you, but you may be surprised when I show you why it's not that strange or foreign to you. Let's look back here at this picture of Raoult's theorem. This is Raoult's theorem. Remember, Raoult's theorem is f of a is f of b, the two y values are the same. And we said, okay, there's some turning point, and the tangent line there is horizontal. The derivative is 0. Let's take this picture, and I want to rotate it. Forget about the axes now. Just look at the rotated picture. This rotated picture is the identical picture I drew over here. I have a curve going from x equal a to x equal b. Okay. Where, by the way I'm twisting is the y values don't have to be the same. Okay. And what did we just say? There's some place where there's a point where the derivative, the slope of the tangent, is parallel to the line connecting the 2 points. You have to think here now as if the x-axis is my pen. You twist yourself. You look at this picture. This picture is the same as Raoult's theorem. It's just that it's been rotated. Raoult's is a generalization. The mean value theorem is a generalization of what Raoult's theorem says. If we take this and spin it and redraw the axis as like the x-axis is now over here. Does everyone see that? This is a very important point, actually. Does everyone see that if I take the picture for Raoult's, I just rotate it, I get the exact picture we just did for the mean value theorem? We're just rotating the picture, not the we're making a new x-axis. We're saying if the x-axis is down here, don't you realize it's the same picture? I'm not convincing people. This is something you really have to see in real life. Okay? It's telling us that the mean value theorem is really a more general form of Raoult's theorem. And that also tells us something else. That in math, when we wanted to prove a more general form of a theorem, we're going to use that theorem as the stepping stone to prove the bigger theorem. In other words, the proof of the mean value theorem is going to depend on using Raoult's theorem in a very intelligent way. But it's really the same thing. It's the same situation. There's something, go home, think about at home. You can read the book a million times. You're not going to see this from the book, okay? This is giving you the insight, hopefully, into what's happening. All right. The proof of the mean value theorem is a very famous proof. I can still remember seeing it for the first time when I took calculus. I took calculus and AP calculus in high school. I can still remember doing this proof then. And it was not so easy to follow. But it's such an important kind of proof, and it brings up another new method of doing proofs that it's worth taking the time to go through it. I'm not going to ask you to memorize and be able to do this proof, but the underlying ideas of what we're going to do are very important, and it's just going to be another way of proving things that are used all the time. I showed you in the example to prove there's exactly one root. We did what's called a proof by contradiction. That's one famous kind of proof. What you're going to see now is another famous kind of proof that you've never seen before, a type you've never seen before. So here's what we're going to do. This is going to sound very strange. We're going to set up a brand new function. And this is the method I'm talking about. There's a method of doing proofs by setting up a new function that has, if we're sneaky enough, has the properties we want to give us the answer we want. So we're going to have a new function called h of x. And h of x is going to be the original function f of x minus the secant line. I'm going to write it like that for 1 second. Minus the function that represents the secant line. Okay? Let me first write out what this looks like, and then I'll show you what it means, which is a fault of the book, doesn't do this. All right. What's the equation of the secant line? Well, it's the equation of a straight line starting at a f of a, ending at b f of b. Okay, so if we use the point slope formula, the equation of the secant line is going to be y minus f of a is equal to the slope m of the secant line times x minus a. I'm using the point slope formula with the point a f of a. And solving for y, I get that y is f of a plus m of the secant times x minus a. We already calculated m of the secant. That's this thing here. So I need to plug that in here. So this is going to start to look real messy very quickly. So let me copy this over. So in other words, h of x is going to be f of x minus, with a big parenthesis. Parentheses are very important, as you've heard me say many times. The equation of the secant line, the y value. So let me write that in. F of a plus the slope of the secant, which is this mess. Let me write that over. F of b minus f of a over b minus a times x minus a. I'm subtracting these two functions. I'm writing out what the function is that represents the straight line, y equal f of a plus m secant times x minus a. And I'm taking the original f of x, which is the curve, and I'm subtracting 2. Okay, this is amazingly opaque and vague, but I'm going to show you geometrically what this really is. This function actually is measuring the distance between the curve and the straight line. In other words, if I take f of x, the y value at some point on the curve, and I subtract the y value on the line, what I'm simply getting is the distance between the curve and the line. That's what this function h of x represents geometrically, really. It's the difference between the distance between the curve and the straight line, which is the y value of the curve minus the y value for the straight line. That's that distance. Everyone got that? The books never tell you that. Do people see that? This is not easy.
The distance of what?
The geometric interpretation of the function h of x is it represents the distance between the curve and the straight line. Pick any point x. The y value for the function is up here. The y value for the straight line is there. If I subtract the y value for the straight line from the y value on the curve, I get the distance between the straight line and the curve at that point.
Okay.
Got it? Everyone see that? You don't need to know that to do the proof. And the first time I ever saw the proof, no one told me that. And the book doesn't tell you that here either. I'm just trying to give you some feel for actually where this comes from. We didn't pull it out of thin air. And there's a very important reason why this particular function is going to be useful, because you may notice at x equal a and x equal b, what's the distance between the curve and the straight line? 0, right? I'm concocting a function that at x equal a is 0 and x equal b is 0. And I'm concocting that function because that's exactly what you need for Raoult's theorem. So there's a great deal of brilliance behind this proof, okay? You don't have to know any of that to do the proof. It was just thrown at me, just like the textbook throws it at you. It's only afterwards that someone explained what's going on here, where it came from, okay? This is not easy. I'm telling you guys, this is not easy. You're not going to be expected to redo this proof. I'm showing it to you because, as I said, this method of setting up a new function to get to the objective you want is used all the time. You just have to have the inspiration of how to do it properly. And when you read in the book, you just read it saying, where the heck did they get this function h from? You know, they pulled that out of thin air. Well, they didn't quite pull it out of thin air. Here's the reasoning. All right. In any event, let us continue with our proof. We're setting up this new function, okay? And let's see what we know about this brand new function, okay? First of all, it's a sum or subtraction of all things that are continuous and differentiable. So we know this function h is certainly going to be continuous on the closed interval AB. It's going to be differentiable on the open interval AB because it's simply the sum of functions or the subtraction of functions that are continuous and differentiable. And let's calculate what h of a equals at the point x equal a. What is h of a? Well, if we plug it in here, we're going to get f of a minus parenthesis f of a plus f of b minus f of a over b minus a times a minus a. I'm just plugging x equal a into the function h. A minus a is 0, so this entire term here is 0. This is f of a minus f of a, that's also 0. So h of a is 0. The function h at the point x equal a equals 0. Yes, that's exactly why we rigged it this way. As I showed you geometrically, that's where the idea comes from. the distance between the curve and the straight line at x equal a is 0. Now let's look at h of b. H of b, just plugging it in, is going to be f of b minus parenthesis f of a plus f of b minus f of a over b minus a times b minus a. I'm just plugging x equal b into the formula for h of x. Okay. Now, this b minus a and this b minus a will cancel out. So we're going to be left with f of b minus f of a minus f of b plus f of a. Remember, this fraction is not a fraction anymore because the b minus a is canceled. And I distribute the minus sign over what's left. F of b minus f of b minus f of a plus f of a, big fat 0. Okay? Well, what do you know? Our function h satisfies the requirements for Raoult's theorem. It's continuous on the closed interval, differentiable on the open interval, and it has the property that h of a equal h of b. That's true because both sides of the equation equal 0. Okay? So Raoult's theorem can now be brought in. Raoult's theorem says there has to be some point c where the derivative is 0 for the function h. So let's first take the derivative of h. Well, the derivative of h, we got to look back to what h is going to be the derivative of the first term, which is f of f prime at x, right? Minus the derivative of f of a is a number. The derivative of the number is 0. Okay. This is a number times x minus a. When you differentiate here, well, if you want to distribute this fraction over x minus this fraction times a, if this is multiplying x, then the derivative is simply the thing multiplying x, right? It's a constant number. F of b minus f of a or b minus a is a number times x. When I take the derivative of that, I just get the number, f of b minus f of a over b minus a. And when I distribute this over a, I get a number times a number minus a number times a number. The derivative of that 0. So this is what h prime of x is. And by Raoult's, there exists a point C in the interval AB where this derivative is 0, where h prime is 0, meaning that at the point C, I have f prime of C minus this number, minus f of B minus f of A over B minus A is 0. And rewriting this, if I add that to both sides, we're left with f of b minus f of a over b minus a is equal to f prime at c. and we did it. Okay? All right. So we have now proved the mean value theorem. So summarizing, what does the mean value theorem say? It says if I have a function continuous on a closed interval, differentiable on open interval, then there must be some place in between the endpoints, which we call x equals c, where the derivative is given by f of b minus f of a over b minus a. Now, this theorem, so as I said, this is an important thing to see how we take a brand new function, we make up a brand new function because we know it's going to lead us to something we can use. It's sneaky, and it's used often. All right, a couple of things about this mean value theorem. Mean value theorem is what we call an existence theorem. It tells us there must be such a point C, but it doesn't tell us anything about how to find it. And usually you cannot find it. You know it must be there. But believe it or not, just knowing it must be there is good enough for most of the uses of the mean value theorem. It forms the bedrock for proving the major theorems in the next chapter and for proving some of the major theorems in Math 201 and endlessly. It's probably one of the most important theorems in calculus, okay? Everyone has got to know how to state the mean value theorem, word for word, okay? I'm not going to ask you to memorize the proof. It's too much, okay? Okay? All right. Now, let's look at a quick example, and then we're going to make some interesting conclusions. Oh, so here's the first example. Suppose the function I'm using is a distance function, and distance in terms of time. You know, like when we do velocity problems, distance in terms of time. So suppose I look at an interval of time from time A to time B, and suppose something is traveling with this distance function, whatever it is. We saw the one for gravity, you know, could be 1/2 GT squared, something like that, whatever it is. I don't care about it. But suppose I have a function for distance as a function of time. And we look at the interval from time A to time B, and the function's continuous and differentiable. Okay? Then the mean value theorem says the following. There must be a time C where f of b minus f of, I'm sorry, s of b minus s of a over b minus a is equal to s prime at c. Let's move this up. And let's see what is the physical interpretation of this thing. What does this tell us? The term on the left, this is the mean value theorem. We're just using the function s of t instead of f of x. This represents your average velocity from time A to time B, right? It's the change of distance, s of b minus f of a, divided by the change in time. So this side is the average velocity. The derivative of the distance function, though, gives us the exact velocity at any instant, the instantaneous velocity. So this side is the velocity at some time t, which is in the interval AB. So what does this practically tell us? Well, it says, suppose I get in a car and I take a trip and I start at 0 miles an hour, something, or whatever it is, and I speed up, and then I stop for a traffic light, and then I speed up and I stop and I get on the highway and I go faster and then I go slower, blah, blah, blah. And I just add up the total distance and divide by the total time. That gives me the average velocity. Let's say the average velocity was 30 miles an hour. The mean value theorem tells us that there had to be some time between the initial time and the ending time where my instantaneous exact velocity occurred, meaning the following. I'm gonna better express this a little more carefully. It tells us that at some point in your trip, your speedometer had to read exactly what the average velocity was for the whole trip. In other words, if my average velocity was 30 miles an hour, it says that at some time during your trip, your speedometer was reading exactly 30. That intuitively makes sense. I mean, if I start at 0 and I accelerate and I slow and I accelerate, intuitively everyone knows that the average is going to be somewhere between the two endpoint extremes. But this is a mathematical proof of that fact, that there has to be some place in your trip where your exact velocity was equal to the average velocity for the whole trip. Okay, there's no way you could start at 0, go up to 20, then accelerate to 60, then come back down to 40, and then up to 60 and back down to 10, up to 20 and go to 0, and find that your average velocity but 30 without you ever having gone through 30. You had to have been at 30 sometime. Okay, so that's a simple little teeny application of this, okay? The average velocity. Okay. Quick little example here. So suppose f of x is equal to 2x squared. I believe this one is actually in the book. Minus 3x plus 1. And we're on the interval 0, 2. And show us that there is a point where the mean value theorem works. In other words, A is 0 here, B is 2. Let's apply the mean value theorem. Okay. The mean value theorem on one side says f of b minus f of a over b minus a. So f of b means I plug in 2. So 2 squared is 4 times 2 is 8. Minus 6 plus 1 over 2 minus 0. That's 2 and 1 is 3 halves. Okay. On the other hand, let's look at the derivative. The derivative is 4x minus 3. And we're told that there has to be some point where this derivative equaled 3 halves in the interval, because this function is continuous and differentiable. In other words, somewhere 4x minus 3 had to equal 3 halves. In other words, 4x is equal to 3 plus 3 halves. This is 6 halves plus 3 halves is 9 halves. So x is equal to 9 over 8, which is 3/4. Okay, that's your point C. So in this particular problem, we were actually able to find the point C that the mean value theorem predicts has to be there. Okay, I calculated f of b minus f of b minus a. I see it's 3/2. The mean value theorem says that the derivative must equal that 3/2 somewhere in the interval. So set the derivative to 3/2, and sure enough, we discover there is such a point, x equals 3/4, which is in the interval as required. But generally speaking, it's not so easy to find C. And as I said, most of the time, we don't even care about C. The only thing we want to know is that there is such a C, that point C exists. Okay? That's a good question, because I messed up. How did that happen? I messed up somewhere. Derivative, that makes the derivative 0.
I don't think it was 3/2.
I must have done something wrong. So f of b, 2 squared is 4 times 2 is 8, minus 6 plus 1, that's 2 and 1 is 3. B minus A is 2, so that's 3/2. Right? And we set the derivative to 3/2, add 3 to both sides, 3 plus 3/2, 3 is the same as 6/2. 6/2 and 3/2 is 9/2.
Shouldn't it be 8 minus 6 plus 1 minus 1?
Oh, it's minus 1. Yeah, you're right. That's where the mistake is. It's minus f of a. When I plug in a, I get 1, but it's minus 1. You're correct. That sign's wrong. That should be a minus sign. Thank you.
No, wait, it should be 8 minus 6 plus 1 minus 1, so it's 2 over 2.
We're plugging in, we're plugging in 0 here, 0 and 0.
Right, but f of b gives you 8 minus 6 plus 1, right?
Oh, you know what I did? I just calculated f of b. I didn't subtract f of a. That's what I was doing here.
Right.
That was the mistake. This is x minus 6 plus 1 is what I had written here. That's f of b. This is a sloppy mistake. Now I got to subtract f of a minus 1, right?
Yeah, I got 2 over 2.
All right. So that becomes 2. 2 over 2 becomes 1. I hope that's right now. All right. Bad move, sloppy error. So that becomes 4x equal 4 and x equal 1. Is that right? Is that right? Yeah, thank you. I forgot to subtract f of a. This is why I tell you, don't do things in your head on exams. It's dangerous. Okay, thank you. Sloppy mistake. I take 2 points off myself. Okay, let me just see how much time we have. All right, now, let me just give you one other last little example. We're running short on time because after this, there are several very important results that come from the mean value theorem, stuff that you need to know. But let me just give you one last example because it's a little bit of a favorite of mine. Let's take the function sine x. Okay. And we're just going to look at it at some interval 0, x. I'm not going to specify what x is right now. Okay, we'll just say x is some small number close to 0 for the moment. So a is 0, b is x. Sine x is continuous and differentiable everywhere. So we can apply the mean value theorem. The mean value theorem again says f of b minus f of a over b minus a. Well, f of b is sine x minus the sine of 0 over x minus 0, which is sine x over x. And we're told there must be some point C where this is the derivative at point C is equal to that. So the derivative of sine x is cosine x, right? So it tells us that sine x over x must equal the cosine for some x equals c, right? But we know that cosine is always stuck between -1 and +1. So we're just looking at the interval 0, x, where everything is positive. So we know that the cosine of c has got to be less than or equal to 1. This is the mean value theorem, which says that sine x over x is less than or equal to 1 when x is close to 0. Another way of saying that is sine x is less than or equal to x. Okay. I'm just doing it for positive x. It's also true if you're on the negative side of 0. That turns out also to be a very, very important relationship that's used very, very heavily. It's once again that approximation that some of you have seen in physics for the pendulum. Sine x and x are very close because sine x over x is less than or equal to 1. If I multiply across by x, I get sine x is less than or equal to x. Okay? So it says sine x and x are very, very close, near 0. You know that because sine x over x, that limit would be 1. But which one is bigger? The ratio sine x over x as x gets near 0, that ratio is close to 1. But which of the two of them is bigger? It tells you that actually x is a little bit bigger than sine x. That turns out to be important in more advanced stuff. Okay? I'm just doing the positive side. That was a filler because I knew I could do that in 2 minutes. All right. It's not that important, but I'm just pointing out some of the things that can be obtained by this. All right. So I'd like to see if we can assign some homework problems. I don't know if I covered enough that I could assign problems on. They said the next thing we're going to be doing is a whole bunch of very important theorems. The last paper. Okay. That's how I remember which is bigger near 0, sine x or x. They're very close together, obviously, because their ratio is approaching 1. All right, now let me just see here. We're now talking about section 3.2. All right. Okay, so we can assign a couple of problems. Okay, so first of all, let's see. Problem number 9. Daniel, you want to try number 9? We're now going around everyone once again. It's been a while since we picked on you. Would you be able to do number 9? It's an easy problem. Daniel, you still here? Don't everyone speak up at once. Let me just see something. Oh, Daniel deserted us. Okay. In that case, how about Molly? Are you here?
Yeah,
Are you here?
yeah.
Oh, okay. Okay. Could you do number 9 then? It's 3.2 number 9.
Sure.
It's an easy problem. It's just applying the mean value theorem.
You said 3.2, right?
3.2 number 9.
Okay.
Okay, next, 3.2 number 15. Okay, this is a little bit harder problem. It's an interesting problem, but harder problem. In math, interesting usually means harder. Okay. Fiola, you want to volunteer for that? Yes? Okay. It's up to you. It's not an easy problem. I'm telling you. You sure? Okay. So that's 3.2 number 15. Okay. And I have one more, number 23. This is also not the easiest problem. I mean, it's not hard once you see it. Once you see it done, but okay, let me just see who else I haven't bothered in a while. Richard, how about you? You still here, Richard?
Yeah.
Okay, we need your expertise for 3.2 number 23.
Okay, cool.
Okay, this is a problem worthy of your ability. Okay, it's a little bit of thinking. There's an example in the book, but it's not that difficult. None of these are that difficult.
Okay.
Okay. Yeah, everything's easy, right? Yeah, for me. Okay. All righty, guys. Look, I freely admit the first time I saw the proof of the mean value theorem, I also sat there saying, where in the world did H come from? It was just an algebraic proof. And that's what I dislike about the way the book presents it. He doesn't give you any insight into this. And it's not that someone pulled it out of thin air. We have 6 minutes. Let me just make one last comment here. And I'm also at the same time going to close this. This is a very important point, actually, that one of my professors always used to say, and it's true, and it's something you should think about. Now, when you see these proofs presented to you, don't get intimidated. Don't look at these proofs and say, my God, not only is it hard to understand, but you have to be so brilliant to come up with these things. The fact of the matter is that these proofs you're looking at, virtually none of them are the work of one person. They're the work of many people that's been refined over 200, 300 years, in some cases 2,000, 3,000 years, like Pythagorean theorem or something. The original versions of these proofs didn't look anywhere near as neat and slick as you see it in the book, okay? It's very rare that there's a major big proof that one person's brilliance came up with. There are some examples, like with Einstein, but it's very rare. So when you're sitting here and you're looking at this, a proof like this, and you're saying, my God, where in the world would anyone ever come up with such a thing at all? The answer is one person didn't come up with such a thing. Okay, it came up as a sum total of many different people putting in many different ideas that finally was synthesized and put together and came up with a final polished result. So don't let yourself be discouraged if you look at this and either say, I barely understand it, and I certainly could never ever have come up with it. You're not supposed to. I mean, you're not going to. And because the original people who came up with this proof it was not a one-man job usually. As I said, it took many, many years. This particular theorem, mean value theorem, took quite a while to prove it and do it properly. It took quite a while. I mentioned the fundamental theorem of algebra at the beginning of the class. That took a very long time, and some of the greatest mathematicians published incorrect proofs. Some of the greatest mathematicians. It wasn't proved until like the mid 1800s, and people had known about it since like the 1500s. They knew it had to be true, but no one could prove it. So don't get intimidated if you see some of these things which just look like, my God, how could I ever do this? You know, you could do it because in the way it was done, which was that it was a sum total of many different people, many different ideas over many, many years being put together and reworked and worked and reworked and reworked until the final polished result came out. When these proofs were first come up with, none of them looked this neat and clean. I mean, I know to you it doesn't look neat and clean, but these are neat and clean. Okay, so don't be intimidated, particularly if you like math and are interested in math and may even be thinking of going into it. Don't be influenced. Don't abandon your thinking just because some of the stuff you're seeing, you look at and you say, my God, it's intimidating. Who could ever do this? I could never do it. That's not true. The proofs you see in the book, these are polished final results. And as I said, it took years and years and years and many, many people in virtually all cases to come up with this nice little compact result you see in the book. Okay? I always thought that was an important piece of advice I got from one of my professors, and I pass it along to you. So don't decide right now that you're not going to take 152, at least for this reason, okay, or something like that. All righty. So I guess we'll see you all on Thursday. Okie doke. All righty. Okay. Let me just take care. Okie doke.